Yeah, hello guys, welcome back to my channel. And then now let's just have a look at the vertical spring extension. So when we have a complicated vertical spring, how we are going to go over the problems. So I just set up a diagram here where I have a natural length. I shaded it just in red color. This is just a natural length of the spring. And then what happened after is now you attach a mass. Okay, when you attach a mass due to gravity, it will fall down, and then it will just stay there. And this position, without any compress or without any stretch, you will just stay at the equilibrium position, which is the red position. And then after that, when it stayed at equilibrium position, because we want it to oscillate, what you're going to do is you're just going to compress it by amplitude A. After you compress it by amplitude of A, this mass is just going to oscillate between these two red lines. Okay, so just going up and then going down and then moving back up and then moving back down, and then just keep doing these oscillations in a circle and a circle and circle, keep repeating its motion, and this is just a simple harmonic motion. And then today we're just going to look at the energy balance for the simple harmonic motion. So first of all, from the natural length to its equilibrium position, this is because of the gravity is pushing it down. So for this mass here, it's experiencing two forces. One is a spring force Kx, and one is gravity mg. Okay. And now we can figure out this distance. The distance from the natural length to the mass, we call it just x naught, just like you can call it x1, x2, whatever you want to call it. And this is my, I'm actually going to call it x equilibrium. Okay, like x naught is my x equilibrium position, and the way to calculate this equilibrium position is just using kx equilibrium equals to mg. Yeah, therefore kx equilibrium just equals to mg k. Yeah. So the equilibrium position just equals mg on k. Okay, that's just the distance away from the natural length. Yeah. Now, when it moves, so let's have a look at each movement. When it moves up, goes to the amplitude position, and then move down, go to the equilibrium position, and then move down again, go to the amplitude position. And position number 4 is just a very random position, just a distance x away from the equilibrium position. So those are the special positions. So so position 1, so position 1, green one is our equilibrium position. Position 2 here is our amplitude position. And then position 3 is the other side of the amplitude position. And then the last one, position 4 here, is any random position. Any random position. Yeah, now I just draw a table here. For each of this position, we're going to look at their kinetic energy, their electric potential energy, and their gravitational potential energy. Yeah. So kinetic energy is just equals to half mv squared. Let's have a look at it here. Yeah. So at equilibrium position, we all know, okay, it vibrates at the highest speed. So this will just be at half v naught squared. Yeah, remember v naught, just v maximum, they're the same. That's just the maximum speed. And at position 2 and position 3, they are changing the directions. Whenever anything changing the direction, the speed will equal 0. If their speed equals 0, position 2 and 3, their kinetic energy will just become 0 joules. Okay, 0, 0 due to speed 0. And then position 4, just at any random velocity, we're just going to call it at velocity v. So this is half mv squared. Okay, so just v, just a random velocity. Now let's have a look at the elastic potential energy. So the elastic potential energy is defined as half k delta x squared, and this delta x is the distance measured from the equilibrium from the natural length. Okay, this is a distance measured from the natural length. So just how far you stretch compared to your natural length position. Okay, yeah. So we know, okay, yeah, we know they all just going to start with a half k something, and half k something squared, half k, and half k. Okay, all we need to work out is what is delta x, what's the distance measured from the natural length. So let's have a look at them one by one. So at the first position, it's very clear. So this is our natural length position. Okay? At the first position, the distance away from the natural length is just going to be x naught. Right? The distance away from the equilibrium position just going to be x naught. So just can quickly write it down. It will just be half k x naught squared. And at the second position, which is over here, so one is measured from the natural length, and we're trying to figure out what is this distance here, and what's this distance here. So if you look at this big blue line is x naught, this small blue line is a. So using this, or probably using a different color too. Yeah. So this big black line is x naught, and this small black line is a. You can see using this big black line minus small black line, we can get the distance away from the natural length, which is x naught minus a. Right, so this distance here, the black circle, is x naught minus a. Yeah. So let's quickly write it down. So this would be x naught minus a. Yeah, x naught minus a is the distance away from the natural length. Yeah. Now let's have a look at position 3. Yeah. So at position 3, we need to zoom out a little. So this is our natural length position. This is our actual position. So the distance away from the natural length, you can see it consists of two parts. One is your x naught, and then one is your amplitude. So using x naught plus amplitude, we can figure out the distance away from the natural length. Okay. So you just plug that in. So this will just be x naught plus a squared. Okay. Yeah. Now let's move on to the last one. At any random position, how do I work out the distance away from the equilibrium position? Yeah. Again, so we know this x here is defined as a distance away from the equilibrium position. So this distance compared to this x naught, right? Yeah. So using x naught minus this little x, this would be the distance away from equilibrium. This black circle would be the distance away from the natural length. So we are just going to use that. Okay. So just going to use x naught minus x. We will be able to figure out this distance here. Okay. So that position here will just be x naught minus x all squared. And then we know, okay, a minus b squared, it's exactly the same as b minus a squared. So there's other way to, so you might want to write it as a half k x minus x naught squared. They will be the same. Anything squared, minus 5 squared and plus 5 squared is all 25. So it doesn't make any difference. The last one is gravitational potential energy. The gravitational potential energy is all based on where you define the zero height is. And in this question, for the simplicity of the calculation, I am just going to define my green line as my height 0. Okay, so this green line is when the height equals 0. This is my reference height line. Okay. This is my reference height, and anything above will have a positive potential energy. Everything below will have a negative potential energy. So the gravitational potential energy just equals to mgh. H is the height measured from the reference position. So this is the height measured from the reference position. So now let's write them down. They all going to be mgh, 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 and then mgh. So the first one is equilibrium position at height equals 0. We just put a big 0 here. And then the second one here, the first amplitude above the green line. So we're just going to put the A here. The next one, position 3, you can see is amplitude below this position. We put a minus A here. And then the last one is just x meters above this m. So we're going to put an x over here. Okay, that's just mgx. So now we have all 4 equations together. And then if you expand them, you will find position 2 and position 3 they are the same. Okay, they're both at equilibrium positions. You don't need to use, you only need to use one of them. Okay, because these 2 equations basically give you the same thing when you simplify. So all we need to know, all we need to use just equation 1, equation 2, and equation 4. Okay. So let's quickly copy it down. Yeah. So from position 1, we have the mechanical energy equals to half k, half mv naught squared plus half k x naught squared. And then from position 2, we have a half k x naught minus a squared, and then plus mga. And then our random position, and this just consists of all 3 terms, half mv squared plus half k x minus x naught squared plus mgx. Okay, plus mgx. Yeah. So we're going to use the first 2 equations together to do the calculations. Okay, yeah. So we have a half mv naught squared plus half k x naught squared equals to half k x naught minus a all squared plus mga. Okay, plus mga. And let's expand this one first. So it's just going to be half k naught squared and then minus a half multiplied by k multiplied by 2x naught a, and 2 and a half cancel, so it just become k x naught a plus a half ka squared plus mga, okay, plus mga. And we also know from the equilibrium position, we know our x naught is defined as mg over k. So we can just replace this. So we can just replace this x naught with mg over k. Okay, and then you can say k and k canceled. This entire term just become minus mga. Right? Minus mga and positive mga. Minus mga and positive mga canceled. You can see there is no gravitational potential energy effect. Okay, there's no gravitational potential energy effect. And then we just have the half kx naught and half kx naught cancelled. So we have half mv squared equals to half ka squared. So half mv squared equals to half ka squared. And you can simplify it, so we get k on m equals to v naught squared on a squared. And this equation is exactly the same as the horizontal spring, because like we said here, the gravitational potential energy get cancelled. Minus and then plus it get cancelled. So there's no net effect for gravitational potential energy. And then now what we're going to do is we're going to find the velocity at random position. So trying to find out this v here. So obviously we're going to use equation 4, and then you can choose to use either equation 1 or equation 2. We prefer to do equation 1 because equation 2 here has an ugly gravitational potential energy. We probably don't want to deal with that. Okay, but you can use either 1, 4, or 2, 4. You get the same answer. Okay, so you can use either 1 match up with 4 or 2 match up with 4, and these 2 will give you the same answer. Okay, and for the simplicity of the calculation, we're just going to use 1 match up with 4. So our equation 1 is half mv naught squared plus k x naught. Okay. And then for our equation 4, it's half mv squared plus k x minus x naught squared plus mgx, plus mgx. Yeah. So that's all the equations. Again, we are going to simplify this middle term first. Okay. So this middle term is half k x squared plus, minus k x naught, and then plus half kx naught squared. Okay. And then we know, this x naught just equals mg on k. So just using the same equation again, plug back into here. Plug back into here, we know x naught is equals to mg on k. K and k cancelled, and then you can see another magical thing happened again. This is minus mgx, here is plus mgx. So the gravitational effect cancelled again. Okay? So the gravitational effect cancelled again. And let's cancel out the two more terms. So we have half kx naught, cancel with this half kx naught. And then overall, we're just left with half mv naught squared equals to half mv squared plus half kx squared. And then cancel out all the halves, we have mv naught squared equals to mv squared plus kx squared. You're trying to find the velocity expression, you are going to make this velocity the subject. Then you're going to make this velocity the subject. So velocity squared just equals to v naught squared minus x squared on a squared multiplied by v naught squared. And then we know from the previous conclusion, k on m is v naught squared on a squared. And we're just going to plug it back into here. Plug it back into here. So we have v naught squared. We have v naught squared, and we are going to use k on m. Replace. Oh, sorry. I just So sorry again. This one here should be k on m. This one here, when you reverse it, it should be k on m. And then we're going to replace this k on m by v naught squared on a squared. Yeah, so I think I just quickly rewrite this stuff again. When you're making v squared the subject, I just stuffed up my algebra. But when you're making v squared the subject, this part should be v naught squared minus k on m x squared. Okay, now it's 100% right. And then we replace k on m by this equation v naught squared on a squared. Okay, plug it back in here. So it's v naught squared minus v naught squared on a squared multiplied by x squared. Okay, now take the square root. So v equals to v naught square root of 1 minus x squared on a squared. So this is the final expression.